Oh, the whole recording is not open. Okay.
I think the YouTube part, the real-time part is still open, or open the mic.
Yeah, I just turn on the mic.
Okay.
小麦听得到吗 She'll reply in 20 seconds. Okay. So, yeah, we were talking about that for stack variable, because this overhead, usually we wanted to have tail recursion, and so let's go back to this example. The reason why we need to keep the stack is because there is a continuation of this computation. For this line, the result is f of 3 plus f of 2, and we need the result of f of 3 and f of 2 to get the final result. So after we have the result of f of 3, it's not the final result. We need to continue to the later part, to adding it to f of 2. That's what I mean by continuation. And if you call a function, the function's return value still have a continuation waiting for it. You cannot just reuse this space. You have to use another stack to avoid polluting the current context. So that's why we need to keep creating new stack. But that being said, what if there are conditions that we know for sure that we can just reuse the stack? Then we don't need to grow a new stack. That's where that's where tail recursion, the condition of tail recursion come from. So if you want to have tail recursion, the conditions usually is the return value is simple value, meaning it's not another function call. And another condition is usually the return value is a pure function call. Yes. So by this I mean that if you have something like f of x equals g of x, or I should write it in a programming term, f of x equals then return g of x, because the result of g of x is the result of f of x. So by the point when we reach g of x, we no longer need to keep the stack that was allocated for f of x, so we can reuse the stack. This avoids the overhead of stack allocation and avoids the possibility of a stack overflow. Okay. And the next kind of dynamic variable is heap dynamic variable. Heap dynamic variable are allocated and deallocated, usually by this is a explicit heap dynamic variable. So these are the variable that's allocated runtime explicitly by the user. And if you have written in C++ or Java, you know this. You have to make sure you allocate memory for the things you want, and make sure you clean it explicitly. And I'm not going to talk too much into this, but because most people here aren't familiar with C++, that kind of language. But these kind of language will have construct design patterns that make sure you don't forget to deallocate memory. So the advantage here is its flexibility, because you can allocate whatever you want in whatever size and whenever you want. But the disadvantage here is also inefficient due to heap storage management. Heap storage management is not as efficient because in order to allocate a heap memory, your program go from application space to kernel space and then back to application space. So it takes a bit more time, and it's unreliable due to pointers. What does this mean is is if we have a linked list, we have something called previous, and then it points to something that's let's say if we have a node, inside the node there is a method called previous, a variable called previous, and previous points to another node that's allocated dynamically into another memory space. Then first is there is no guarantee that these two nodes live nearby to each other in the actual memory layout. One may be in memory location 100, another may be in memory location 1000. So there is no way for your operating system to cache it for you. So the access time might be slow. And it might be possible that when a user, when the program deallocate the memory here, the program forget to follow the pointer to here and deallocate this part also, and then this part becomes garbage. So this is the potential problem. So a good design pattern need to be imposed to make sure all memories can be deallocated. Okay. And here there is also implicit heap dynamic variable. It means they are a heap variable, but you don't allocate it by yourself. So if you write Python, JavaScript, or Scala, most of the heap variable or all heap variable you are going to encounter are implicit heap dynamic variable, because you never explicitly allocate a block of memory before you do something. It's always allocated by your program. But if that is the case, then we have a problem of how do you collect those memories back. But we'll go to that problem later. But for now, let's look at why we might need implicit heap dynamic variable. Okay. So this is I think the slide is not updated. This is a standard function, a pretty common function that you see in a machine learning application. You have a function called optimizer, and in this optimizer you give it a hyperparameter that doesn't actually calculate the loss for you, but then it returns a function, the actual loss function. The actual loss function takes into two values and calculate the nth degree distance between this x might be the actual value and y might be the predicted value. And if you're a data scientist, you know that the larger this n is, we are more sensitive to outlier, and the more close to 1 this n is, we are less sensitive to outlier. So this is a pretty common function. Let's see if we have if we do something like this. If we define, or if we have a variable loss equals optimizer 2, that means we want a second degree loss, and then we further pass this loss inside some model, not fit, and it has some, we pass in some x, y, and the loss function. So this could be some standard machine learning code. For this part, if we look at the memory layout, when we call optimizer, it grows a stack here. We first grow a stack for optimizer, and inside optimizer there is this n equals 2. But then optimizer returns to this variable called loss. Now, what if at the moment function return we deallocate the stack, then this n is no longer accessible. So when you call fit, fit requires the calculation of this part, requires the knowledge of n can no longer be found. So that's why we in this case we need to keep the stack. But if we need to keep the stack, then we have multiple stack, because now we are calling another function again. So this will have to be kept in the heap space, and that's why we have the implicit heap dynamic variable. And usually in functional programming, because it's allowed that you return a function. Oh, in functional programming, it's called curry function. When you have a higher order function, a function that returns a function, and I think in Python or JavaScript, you also hear the word closure. Usually, that's what's it about. Higher order function, curry function, closure, they are all similar things. It means a function has a context that's wrapped by another function. So this would be the case where you might need implicit heap dynamic variable. So far only for the explaining why we need this kind of variable, but then the problem is how do we collect the garbage resulted from these kind of implicit heap dynamic variable. We will look at JavaScript. We look at JavaScript's garbage collection, for example, only. And before that, let's look at some other JavaScript example. So the way JavaScript handles string is JavaScript store constant string in heap, implicit heap dynamic variable. That's how JavaScript store a constant string. So if you have a VARS equals this string, and if you have VARY equals the exact same string, you will actually duplicate the memory. So if you don't want to duplicate the memory, you need to assign S to Y. That's how JavaScript's constant string work. And JavaScript object also will allocate a heap dynamic variable, and its array also heap dynamic variable, and yeah. Okay, here, if you have a string, it's in heap dynamic variable, and when you create a substring from this original string, it also create a new string that doesn't share whole. Semantically, it's a new string, but it might optimize it away by allocating the same set of memory. So what that means is it's important to know the semantic meaning of a language, because even if JavaScript runtime engine decide to share the memory, they need to implement a mechanism called copy on the fly, because semantically speaking, they are separate variable. They are separate, meaning if you change one thing in place, it cannot affect the other. But if they decide to share the same memory block, then changing one variable would affect the other. So they need to have a mechanism to decide to copy the variable once the memory block is changed. Yes, but I will. Yeah, let's look at how GC could work first. Okay, so as you can see, JavaScript allocates a lot of dynamic heap variable. They might allocate something that points to something, and they might have and there might be another block here. So the way in the very old version of GC, a mechanism to do garbage collection is called reference counting. It keep counts if each memory location is referenced by the other by the other place, is used by some other memory location. So in this example, you would have this variable would be this variable is used by some other variable, and this variable is also used by some other variable, and they are all like coupled together. But what if one day we delete this variable? Then this memory cell no longer have no one is referencing to this memory block. So the runtime engine would know that we can also do memory collect. We can also do garbage collection on this block. That's the rough idea of reference counting. But the problem with reference counting is if you have some data structure that's referencing itself, then that data structure can never be garbage collected. So this is an example where you create a DOM first, and then you have a member value of the DOM referencing to itself, so that as long as this circular reference is not broken up, the reference counting GC can never garbage collect this diff. So if this diff has lots of data, it will always sit in the memory. So that's the problem with reference counting. But this reference counting mechanism is ancient, and usually now garbage collection don't use reference counting. They use something called mark and sweep algorithm. It requires that application defines a route, and it goes from the route to see what are the values that it's still reachable from the route, and whatever values that's not reachable from the route, it can be deallocated. So even if we have something that's referencing itself here, the garbage collector can know that this can be deallocated. Yeah, and yes, so still take a lot of time. I think that's it for the binding part. The main takeaway I hope you get is just when you write a program, you want to understand when does the variable name binds to the value, and how do you get when you reason about a program, when you reason about a piece of code, are you able to know very clearly what these values are before you actually try to run it and test it out? And if you know the binding and the next concept scope, it would kind of help you prepare to learn a lot of new programming language without confusion. Yes, and maybe we take 10-minute break. Yes. Oh, and if I make any mistake about commenting on JavaScript, please let me know, because I don't write JavaScript myself. I just use them as example in this lecture. Yes.
我刚观察，ES6开始有支援 static variable。
哦，是哦，
对对对，
是真的 static 吗？就是 browser 会支援。
browser 要看版本，就是看那个 browser 版本。对，然后但它底层其实是假资源哦，其实。
对，因为一种是我们只是需要这样的 design pattern 嘛，那这样有资源就好。可是另外一种是为了要做优化。如果要做优化的话，
我不知道它底层有没有优化，就是但它的写法确实 就是要写 static 的。
嗯，
可是他之前也有类似的写法，但是就是你可以直接写一个 object， 然后把它就以前用 prototype 的写法，它是可以做成 static 的样子。
嗯，
等于说它额外衍生出来的 instance 都可以用到那一个 variable。
哦，
对，它在执行之前就可以跑到那个，这样应该算 static variable 的定义。在实际上 LK 之前，它就可以使用那一个 variable 的 value。
哦，
这是我认知到的，但我不知道。
这样子，LK 之前就可以使用是什么意思？
就是举例来说，它可以写一个变数，假设叫 foo，
嗯，
然后它可以先写好 foo 点bar 等于1。
嗯，
好，那这个 foo 它本身其实也是一个 constructor， 它可以写，我们可以写a 等于 foo 刮5，然后 a 点 bar 印出来会是1。
嗯，
对，然后也可以直接写 foo 点 bar 印出来也是1。
哦，
对，它之前就有这样的写法。对，但我不知道它底层是不是真的每一个，像我刚刚说的 A 等于 foo 刮5嘛，跟 B 等于 foo 刮5，我不知道它的 A 跟 B 它内部的 bar 是不是同一个 B 啊？
不过真的要说的话，底层应该是，
它搞不好
应该是做不太到吧？
我不知道它底层有没有，因为像
是因为一个 browser 都已经跑起来了。
对啊，
所以它一定要去 load 你的 JavaScript runtime 嘛。
对啊，这应该是本质上就做不到。
对，所以本质上就
做
不到。
它其实感觉好像做到，但实际上只是
但 Node backend 的 Node 我不知道做不做得到。
应该也做不到，因为他们都是 runtime。
哦。
因为它是跑的时候本身就先把 code 都读进去。
哦。
对啊，所以应该是不太好。
那 WebAssembly 是什么概念啊？WebAssembly 是
完全不会，WebAssembly 完全没写过。
学长，我有讲错什么吗？
他都这样说，我才是。
看来就是学长。
没有。
我刚才要跟你讲，但我忘记。
我今天例子很多都用 JavaScript， 因为 JavaScript 真的是一个很有趣的语言。
真的。没错。
这个有趣可以是正面的，也可以是负面的。
哦，我想问那个啦，我想问 Swift 那个 Swift and Cake
这个吗？
对啊。Market Swift。对，我刚没有听懂，我只听得懂说一个是自己连自己会被当 garbage， 一个不会。
就是任何的 graph， 不管它是不是 cyclic 的，就是你可以把这种 reference 关系想象成一个 cyclic， 一个 direction 的 graph 的概念嘛。那这个 graph 不管有没有是 cyclic， 其实都有演算法有办法去从某个点去出发，然后去看到它可以 reach 到所有的点。就是譬如他走过这个点之后，就会先给他一个 mark 这样子，这个 mark 过了，然后再往这边走，这个 mark 过了，
然后
往这边走，
没有被 mark 过就会清掉这样。
对再往这边走就发现这个 mark 过了嘛，就不看了，然后就反正这个演算法是可以 terminate 的。
那他怎么样去？就是因为这样子的 graph 可能会有多个嘛，就是我的意思说，
所以你要 define 出发点。
那它怎么 define？
所以 JavaScript 的出发点就是就是你的那个 root 的 document。对，就是你的应该是我不知道
是哪个。可是你那个算是动的出发点，但如果你用 Node 这一来讲，它就没有所谓的出发点。
应该还是有吧，
就
像 main function 的概念。
你说像 main function，它的 entry point。
对，因为你还是有 entry point。然后 entry point 会长出一堆 stack， 然后这所有人就是都聚找了去。
所以最后还是从它的那个入 entry point 去往下。
对，因为 Scala 也是这个样子。对。对，所以这种方法的话，你没办法手动去叫，通常你不会手动去叫 garbage collect， 通常你不会手动去做。
那你说那前面那种方法为什么？你说那为什么 counting 呢？对啊，前面的 reference counting 的话，跟它的差别是什么？听起来我觉得只是他在说一个是记录它被几个东西。
我刚好像听到就是动那边会有一些问题存在。reference counting。
你说 reference， 你说这个，
前面应该是在它。
没关系。
这个嘛，
对，
就是这个例子只是说以这个 div 来说，它是 reference 它自己。对啊，所以
它 counting 是1，
他就知道它。
对。其实这也是，就是如果是 functional programming 这种状况不可能发生，因为 functional programming 发生不了 circular 的 data structure。对，因为你 create 了 A， 不可能又让它 point 自己。因为你在 creation 的时候 A 还不存在，等到它存在了之后，你已经没有办法再改它了，所以 functional programming 不会有 circular 的 data structure， 所以它也不会有 A point 的 B point A， 这种都不可能发生。对。 想喝水。
写那个 Our Sky 的题目，它也是考 scope，
可以喝，我还没喝。
然后你就教
这个我还没喝。
然后就是那个 for， 它 for 里面封装，然后我知道讨厌这种题，但我每次看，然后他就是叫你去 debug， 你就底下写说我不会讲戏。
哇，我看你剩下可不可以4
把
分钟
讲完，然后写 let， 打过。对啊，我不会这样写。回答他，反正他是要考你懂不懂这也是可能懂。你说不懂啊？我今天2种真的好好笑。
没有了，你没有了吗？
嗯？
你没有了吗？
什么没有了？
你没有杯子了吗？
有啊有啊，去拿一下好了。 好，那我们差不多开始喽。
需要叫Chloe吗？
Okay, and so we what we went through was actually just we actually only went through two topics. We talked about static variable and dynamic variable, and we talked about the pros and cons. And for dynamic variable, there are explicit dynamic heap variable and implicit dynamic heap variable and dynamic stack variable. So there are three kinds of dynamic variable, and so we actually only went through two major topic, two kind of variable. And for dynamic variable, there are three kinds. And now let's talk about scoping. Scoping is something that's important to know how to resolve a variable if it's currently not visible in the current scope. So a scope of a variable is the range of program text over which it is visible. That's the definition of scope. So something we encounter interestingly in Python, if you do something like this, okay, x equals 1. Oh no, sorry, not this. If you write something like if true x equals 1. Oh no, Python has to change line. X equals 1, and then you print x here. In Python, this actually work. I didn't look up Python's syntax to verify if this is legal, but this works this works in a lot of Python. If you write a program like this and just run it with Python interpreter, it would work. But so in Mobago, we write our backend code with Python, and we need to Cythonize it into C to make an encryption on it. So it often happens that our Python code runs this way. But once we Cythonize it into C, it complains about a variable not found. In this print function, it complains about variable not found after we Cythonize it, because if this program is written in C, you would have if true, and then you have a bracket here, and then you have something like x equals 1. I think it's like int x equals 1. So in a C program, the scope of x is only limited by the immediate closing left and right bracket. So if you have a print that is outside this bracket x, this x is no longer visible for the print here. So C and Python have different scoping, and apparently the package Cythonize didn't do that very well. But the problem is it's kind of impossible for that package to do it very, very well, because the way Python does this scoping is very strange. So this is just a brief example to talk about scoping. It's the range of program text over which a variable can be visible. That's the scope of a variable. And now in the old times we have there are two major scoping rules. One is static scoping, another is dynamic scoping. And I'm talking about this mainly for a history lesson, because all of the every language that you are going to encounter nowadays is static scoping. You are not going to see any dynamic scoping language anymore. But for languages like dynamic scoping, it include Perl. Perl was very, very popular in doing the system management and writing system program. But nowadays it's more obsolete now. Okay, and a static scoping is the scoping architecture is determined by the layout of program at compile time. And when we cannot find a variable, we search the block sequence until variable is found. A block sequence is the program layout at compile time, and dynamic scoping is determined by the calling sequence at runtime. So we search a variable if it's not found by the calling sequence until a variable is found. These are just a strict definition, but let's give some examples here. This is a JavaScript program, and if you are a JavaScript programmer, you should know what this will print. It's important. So so we have a function foo. It logs a, where a is not found, but it's okay because it's only in the function definition. It's not executed yet. And we have a bar that calls foo. Before it calls foo, it assigns a to 3. And then we have a global variable a, that's 2. Now we call bar here. And hey, Chloe, do you know if it will print 2 or 3? So you call bar here, and then foo here, a. So does this a resolve to this a, or this a? Ta-da! Okay, so the answer is 2. The answer is 2. This is a example of static scoping, because if this a is not found here, it resolves to its immediate upper scope. So this function is defined here. This is the scope under the function, and the immediate upper scope would be the global scope already. So this a is here. This a is only in the scope of this function, which is in parallel scope of this function. So they are not in the same. Like this is not the parenting scope of this one. If we determine the scope at compile time by programming layout, so the upper scope of this function would be global scope, and the global variable a is 2. So if you write a program like this, it will give you 2. So to be clear, JavaScript does not in fact have dynamic scope. It has lexical scope, but But if you written the older JavaScript in the older React syntax, a lot of time you find that you have to wrap the self reference. That's because the way JavaScript resolves this variable is more interesting. It resolves this more like dynamic mechanism. But JavaScript in general, it's still a static scoping language. Okay. So if you want to learn whether a language is dynamic scoping or static scoping, just write something like this. If it print 2, it's static scoping. If it print 3, it's dynamic scoping. It's a pretty easy test. Now let's look at this piece of JavaScript program. Just to clarify, this piece of program has nothing to do with what I'm going to say today. It's just a really strange JavaScript behavior, and it doesn't really fit into dynamic scoping or static scoping. So if in JavaScript, if you write a function, if you write a object, the object's ID is awesome, and this object has a member function cool. This member function cool will print out its ID. And in the global scope, you also have an ID that's not awesome. And if you call the object.cool, it's awesome here. It will print awesome, which is this awesome. But if you call this like set timeout, this means we put this function. We will register this function into we'll put it into you can say a queue, but we will not run it. We wait until after 100 milliseconds, then we run the function. But this time it will print not awesome. And yeah, so this is strange. If we don't have this example, if we only look at this example, we would be tempted to think that JavaScript is dynamic scoping, because it resolves the variable at the calling sequence of the scope. Instead of looking at the defined sequence, instead of resolve the variable in terms of its program layout. But in this case, it's more strange, because if we call it differently, we realize it's resolving this ID variable differently. So the reason this happened is because JavaScript has a very strange resolution of this. In JavaScript, this doesn't represent the object itself. This represents the caller of the function. The reason why JavaScript need to define things this way is because it's quite common for a front-end program to register an action hook to some component, and when the action hook is triggered, it wants to access the attribute of that component. That's why JavaScript was designed this way. This is very strange. But then when JavaScript become more advanced with all the React library and OOP design, this resolution of this becomes very strange. So yeah, so I lost the example here, but there was a period where JavaScript you have to remember to wrap around this variable by another variable. Otherwise, your React program will act all strange. Yeah. Okay. So that's dynamic programming. Dynamic scoping. Sorry, that's dynamic scoping. So it has very few pro, I would say. It helps communication between sub-programs. This is the only pro I can find, and it's actually a very bad one. it just is a very irresponsible way of saying that dynamic dynamic scoping is good, because in a dynamic scoping it allows you to just create variables everywhere and call functions randomly, and so this would be an example. You can write a function p that uses this variable n, yet the n is not defined in the scope here, and it can be defined whenever you call p, right before you call p. But the problem is, why on earth would we ever need this kind of program? You can just pass p inside. You can just pass n as a variable inside p, and this kind of program is hard to read, because when someone reads the program p, he doesn't know where n is, and this function q can be defined in a completely separate file, completely separate module, so it makes the program very, very hard to read. And another problem is it must be dynamically type checked, because let's say here, if we resolve okay, let's say if the log function requires you to input something that's a integer, and this is double, and this is actually I'm gonna write another piece of program here. So if we have foo, if we have a f that only takes into int, and it does something, and then we have a g. G does nothing except calls f of n, and then we have g1. And in g1 we have n equals a string, and then we call f of n. We call g. We call and then we call g, and then we have g2. This n equals 1, and then we call g. So this example is just illegal in a static scoping language, but this piece of example code is legal in a dynamic scope language, because by the time you call g1, g1 then calls g then calls f. So when g try to call f, that's the time when it needs the n variable, but it realizes n is not found, so it looks up to its calling scope, its caller, which is g, and inside this inside the scope here it finds n, and n equals this string. So but the problem is now f requires n as input, and the input n as type int, so it throws an error here at runtime. But at compile time, you cannot know if this you cannot know if this is going to be correct, because when you compile the function g, it has no idea of knowing where this n come from, so it doesn't know the type of n, so it cannot do compile time type checking. So that's another bad thing about dynamic type. And it can also take a very long time to search a variable, because remember recursion, you can have like 100 layers of a function call, and when you look up 50 layers and still don't find your variable, there is no way to say that you won't find it in the 51st time. So you really have to look up all the time until you reach the root of the problem, which is usually the entry point of the program. and so it's very inefficient. It's very hard to read, and it cannot do a compile time type check. So dynamic scoping has been something that's people don't choose it nowadays. Even the JavaScript, this behavior is changed in ES5. It's changed to be more like static scoping in ES5. On the premise that you use ES5 class syntax, because you can still write ES5 this in the old way. Okay, so onto static scoping. And this is the scoping that all of you are more familiar with, because every language you learn nowadays use static scoping. So I'm just gonna go to the example here. If I write a program, a main function here, and inside we have A and B function, and inside then we also have sub block. This would be the how do I say that? This would be the scope resolution hierarchy. So that means if C have some variable that is not in scope C, it look up A, and if it doesn't find it in A, it further look up in main function. And if D has a variable that's not found here, it look up and then look up. So D will not find something in E, D will not find something in B, and this would be the way static scoping work. So pretty straightforward. But still, in a statically scoped language, there are some variant as to how many scope is allowed. One is monolithic scope structure, where you can only have one global scope. And unfortunately, assembly language is like that. So no one writes assembly language now. And you have flat block structure. That means you can only have one or two nesting level. The old C++ syntax is like that. So that means in C++ you can have a main scope, and then you define a function here. You cannot define another function inside this function. And remember, the reason why is because C++ kept the function call mechanism with a stack variable. So if you have a syntax like this, you could be returning G, function G, and that would result in if you return function G, G might reference something in F, and by the time function F return, you cannot collect the stack. So you have to implement it in a heap dynamic variable in order to do more than one layer of function scope. So C++ was implemented this way, and it still hasn't changed. So the way C++ supports curry function is by a hack. If you want to return another function inside, you need to create a class that support function call interface. So you create a class and return the class, and you can use the class like a function. So that's how C++, starting from C++ 11, allow you to do multiple layer of scoping. So in most modern language, you see it support nested block structure. But why do we distinguish between the two is because usually if a language originally only support flat block structure, but as the language develop, it start to support the nested block structure, you can expect their support of nested block structure is going to be very inefficient, because usually the way they have to do it is by some hack that's allocating a lot of extra class and variable to do so. So, yeah, nowadays if you just don't care about efficiency, most languages support nested block structure. So that's static scoping. And it has many pros. Yeah, this information hiding refers to if I have something x in C, I expect this x never pollute the scope in B or E, even if they call the function C, or even if at this scope they call function C. You don't worry that this x is polluted by other place, and also it can be statically type checked because the scoping is determined by the program layout. So by compile time you can already check the type, and it usually takes shorter time to locate a variable because it's not when you write a program, you usually don't write it more than 5 layers. Usually don't not more than 3. But when you do function call, it's easily get to like 50, 100 call stack. And then okay, so it from here it sounds like static scoping is perfect, but let's look at this example here about what might be the problem of static scoping. So this picture defines the visibility map. It means how do I okay, it means if you are in scope A, you can call function C and function D, and if you are in scope B, you can call function A. If you are in scope E, you can call function B. This is the okay, sorry, let me say it again. Below is the legal function call picture, and this is the if I just draw the hierarchy as a direction graph, it looks very simple, but in practice it's possible that because in the block E, you can go up your scope resolution can go 1 layer up and can also go 1 layer up, and inside this layer we do have both A and B. So that's why here in the block scope E, you can call itself, you can call B, and you can even call function A. So it has the potential call picture can still be very complicated in the static scoping. But the reason why we want to draw this picture is because suppose we have these if our specification change, which happens a lot if you work in a company, if the specification change, let's say now D must access some data in B. Let's go back to the previous slide. So if you look at the picture here, currently D have no access to B. This is the current picture. And what happens if D has to access something in B? Let me yeah. So one possibility is you move this D all the way down to here. So if D wants some access to B, then you can move D to the block here. That's one possibility. But if you look at this potential call picture, D probably is accessed by A, and D probably accesses C. So if you move D to this block, then this A could be broken, and D inside D when D reference C, D could also be broken. So that's the problem of if you want to move D under B, then you need to take into consideration of all those situations too. And so this would probably be not be a good way. Okay, so you can put D in B. And another option, you can let B enclose A. So that would be a... Ooh. Yeah. Okay, because now the problem is D want to access B. But from static scoping, D can go up one layer, A. So if you make sure A also enclose B, then D can access B. So that would be another possibility of doing the program refactor. But then, you also change the scope hierarchy, and if there is something in main that want to call A, it now have to call A through first calling something in B. So you are breaking things up again. So the solution would be you need to move data that's common from B that D need to main. Okay, so that would be in this picture here. Okay, so if the problem we have is D need access to B, then we actually need to move the common variable that's both in B and D outside to their immediate parent here. That's the proper way of doing the refactor. So with static scoping, the benefit is variable resolution is now more robust and more logical, more reasonable. But then it lays on programmers' responsibility to design reasonable information hierarchy. So that's with the static scoping, that's programmer is forced to think things through instead of just writing pieces of program that is loosely coupled together. Okay, so that's for static scoping. And another very little subtopic is namespace. Some language divide names into separate namespaces so that names in different namespaces don't interfere with each other. So you don't have to design too complicated scoping rule. Like here, in JavaScript, function name and variable name are in different scope. So you can write a program like you write a function f of x, f equals f of x is something just return x, and then you have a variable f equals f. This is legal because when this variable because they live in different scope, but in Scala it's illegal. In Scala it's illegal because so if you write a program here, a compiler will complain that this f is already this f either this f is already taken, or you cannot recursively define these two f. So this would be different because the variable live in different namespace. And also we can look at binding time. So this looks strange. VARG equals G, although this G cannot resolve. But this works in JavaScript. It will just tell you that G is undefined, because when JavaScript is resolving this variable G, it says it is resolving it here, it cannot find it. So if it cannot find it, it resolves to undefined. So this G become undefined after you run this line. But in Scala, it's a bit different. In Scala, if you write something like this, this G is visible here. So when it's trying to resolve like VALG equals G, this G resolve to this G, which is then uninitialized. So both code are wrong, but they are wrong for different reason. This is the different attributes. Okay, then I think that's it for today. And thank you for participating. Oh, and did anyone did homework from 2 weeks ago? Okay. Then we really have nothing to discuss then. So I'll end the online lecture now. And if you have any question concerning to today's lecture or last lecture's homework, feel free to stay and discuss. The Mobego office is